Do you guys want to know why? I mean, I don't know. So why? Because your goal is to have the total amount of cables you lay out to be the smallest, right? And so in order to do that, and you have to connect every house. So I guess we could try to do a proof that there is some edge that we should have included that we don't include in the minimum spanning tree. That's how you would prove that you're using the right algorithm. So assume you have a minimum spanning tree for correct. I'm not asking you for a proof here, but we can do it. Assume you have a minimum spanning tree that connects all the houses X, Y, and then let's say that we claim that we should have used the edge XY instead of XU, YU, UY. But how would you have connected U in that case? I think this one's hard to prove, you just gotta go. I don't know, I have to think about how to prove it, but it is minimum spanning tree.
So you would just have to state
Yes.
your guess
What,
of which one
yes.
you would say briefly.
Yes.
The algorithm design part, like 7, doesn't actually involve writing out an algorithm. The only part of this final was to actually write out your own algorithm.
Was proof.
Proof it.
Yeah, yeah. Algorithm design question is more like, you've seen all these problems, right? And now you're in a real world and you're faced with, you know, a different problem. Which algorithm would you use of the set that you've seen to solve the problem? So you could have to modify. So for example, in problem 1, or even though you're not doing network flow, in the network flow question where the kids are walking, so it's a design question, but you're not designing network flow. What you're doing is you're augmenting your input to solve using network flow. So I guess when I say algorithm design, what I mean is that I've given you this arsenal of algorithms. Now you're faced with a problem. You know, how do you augment your problem to solve with this arsenal? And so that's going to hold for B as well. Go ahead.
In a minimum spanning tree problem where we are faced with algorithm design, is it possible to, can you tell us how to prove they are connected components in a MST, because that would definitely show that this is the minimum cost.
You're saying for this question that there are
for any minimum spanning tree, if you prove that minimum spanning tree has the most strongly connected components, that means that you are minimizing any cost or any root or any weights on the minimum spanning tree, right?
So strongly connected components means that they're all fully connected.
Yeah. And
so that there's an edge between everything, which there is in this graph.
Yeah.
So you're saying if I prove that I have a minimum spanning tree on a graph that is strongly connected, then what?
Then it implies that we would have the minimum cost, like we would have the minimum number of edges for all the nodes.
Minimum edges.
Connecting the nodes.
Connecting all the nodes.
Yes, and that would be for any.
I mean, that makes sense, because basically, maybe it's a pigeonhole, if it's fully connected in a triangle, you're always going to choose the two. So you're always going to choose the two edges that are smallest, right?
Yeah.
So in order to connect 3 nodes, you have to have 2 edges. And so the question is, which 2 edges do you choose? Well, if you choose the minimum ones, you have your, minimum way to connect all three nodes. So maybe induction is the way you would prove the algorithm. You'd say, start with 3 cities or 3 houses. Assume that for 3 houses you have, minimum spanning tree, and that holds, or even you could do 2 houses, and then you go, okay, assume for k minus 1 houses, yes, it's induction. Sorry guys, induction always solves everything because it allows you to say, like, assume it holds, something holds for k houses. Look at k minus 1. I mean k plus 1. And here's my k plus 1 house. And I just need to connect that house to everybody else, right, with 1 edge. So, assuming that that edge is not the minimum, and then showing that it has to be the minimum. Okay, anyway, so that's great. Keep always induction in the back of your head for life. It's super helpful. Okay, next question. Suppose you have roads between cities, of each of which take $1 toll. Find the cheapest route from source city to every other city, given that the cost of each road is 1. So what algorithm would you use for this problem? What's the most efficient algorithm? Dijkstra's? People are saying? Yes. So actually breadth first search is the most efficient because it finds the distance between a source and all other nodes in B plus B time.
What question is that? What question is that?
B of the design, algorithm design. Yeah.
Can you prove why we chose the algorithm?
I don't think I asked that, right? Do I? Just.
This is justify. Yeah, but I thought.
I think in describing, it's enough to say that, this is, I can create a graph G with weights 1, and this is known that BFS, it is known that BFS finds the shortest distance from a source for weight 1. So that's justification. But you can take for granted that BFS, everything you know about BFS, CFS, you can take this for granted. Hold on. Give me a moment. I'm dying.